Welcome you all again. So now we are proceeding for the next session, that is day one, lecture one. Before that, I would like to give a brief introduction about our host faculty, Dr. Pankaj Kalita. Dr. Pankaj Kalita is an associate professor in the School of Energy Science and Engineering, Indian Institute of Technology, Guwahati. His current areas of research include solar energy conversion, thermochemical and biochemical conversion, energy management, energy storage, and integration of renewable energy for remote electrification. He has published more than 100 articles in various peer-reviewed journals and conferences with a Scopus H index of 23. Also, he has successfully supervised almost 10 PhD students. He has also contributed many chapters in different book volumes. Further, he has edited 4 book volumes so far. He has successfully implemented several research projects funded by different government and private agencies in the fields of energy generation, energy management, energy modeling, solar power plant design, energy testing, etc. He is currently offering 2 MOOCs under SWAYAM NPTEL in solar energy engineering and technology and sustainable power generation systems. So with that, I am inviting Dr. Kalita to take the lecture one, and over to you, sir. Thank you.
So this lecture will continue for 2 hours, and then we'll have 1.5 hour, probably very close to 2 hours, what is called a tutorial. Okay, so let's see how fast we can go, and it's a very long presentation, because as you can see in the slide, content like solar geometry, fundamentals, design of solar thermal collectors are there. So mostly in these presentations we are going to address the very fundamental things required for designing a flat plate collector. Okay, so before we start our formal presentations on the topic what is mentioned in the title slide, so we need to know, like, why do we need energy, what is the demand, and then what is happening in a global perspective if we say the demand and then the kind of fuel we are burning for generating energy. Then the climate change and adverse effect, then the fundamentals of thermal collectors and its classification, then propagation of solar radiation geometry, how radiation can be estimated, then thermal energy storage, and then finally various applications of solar collectors. So now let us see the progress of energy use. If we see the evolution of power generation, it's long back, 200,000 BC, when control fire was invented. Okay, then slowly we move towards use of coal for heating and cooling applications or cooking applications. Then we have coal power plants. Then we can see first hydroelectric power plant was commercialized in about 1882s. And then if you go down, then about 1888 we can see the power generation from wind turbines, right? And then we have first geothermal district heating system in 1892. And then now what we are looking for is really a sustainable power generation system, okay, because of many reasons, right? And also you can see how this demand is increasing globally. And if you see the entire requirement of energy, it actually mostly comes from these fossil based fuels. Okay, so still we can say it is more than 65% energy is coming from fossil based fuel, right? And also we talked about the quality of life, like human development index. So this human development index is related to amount of power or energy you consume, right, in kilowatt hour. So that means when we talk about quality of life, that means we are actually consuming more fuel for increasing the comfort and quality of life, right? Then we'll see what happens if this is the case. And this is the scenario for Indian context, and this is a very recent data. You can see the contribution from coal, gas, lignite and diesel is it is about close to 60%, and then we'll have solar about 21.2%, then wind about 10.4, hydro is 10.2, and rest is very minimal, but contribution is there. Okay, but what my concern is like this part. Okay, so this is not. So coal part and then fossil part, okay, it contributes about 60%. Okay. Now we need energy production. That means we need to burn, because mostly energy is coming from fossil based fuel, and that leads to actually global warming and greenhouse gas emission to the earth atmosphere, right? And this is the share of carbon dioxide emission by different countries. As you can see here, China is taking the driver's seats, and then we are also not far behind, and then USA and other shares you can see here. Okay. Now this curve is known as killing curve, generated by Mauna Loa Observatory in Hawaii in USA. Okay. So what information you will get here, this carbon dioxide concentration is increasing with years. So if you see about so 1750, it was so it's close to 280. Okay, so safe limit of carbon dioxide in the earth atmosphere is 350 ppm. Right, so it was far below. It was very, very comfortable. Then when this industrial revolution starts, and you can see the rise in carbon dioxide level. So if you magnify this part, the latter part after 2000, you can see here this kind of pattern. Okay. It's very, very high, and it crosses 420. So this is a very recent data, and it was in 2 days back I have taken this data. It is about 426.71 ppm. So already we are in a very dangerous state. Okay, we need to take measure. What are the technologies we can use to reduce those carbon dioxide in our atmosphere? So as you see, climate change, there are various reports on melting of glaciers, right? Then you can say a rise in global warming. Here you can see at the top of earth what we have on the thermometer report, and it shows about rise in temperature. Then rising sea level, unexpected floods, and then adverse climatic conditions, burning forest, and then drought, you cannot cultivate properly. So there are various indicators what you can say this climate change is really occurring, and it is very, very significant. We can see the visible changes, right? Now what is required for us is renewable energy systems. Of course we cannot remove fossil fuel in a day, but slowly you can actually replace these coal based power plants or maybe other fossil based power plants. So it may be solar PV, it may be solar thermal, it may be wind, it may be hydro, it may be biomass resources, or it may be some hybrid systems, it may be ocean, it may be OTEC, okay, it may be wave, or it may be geothermal, or it may be integration of renewable energy systems. So we need appropriate technology based on the resources available. Okay, so it's not something like always we need to build very big unit. In my opinion, we need to optimize it based on the requirement, and we need to have all the technologies in board for sustainability. Now if you see solar thermal global scenario, you can see in the net, and this is the source from where I have taken this data. So it normally tells about area, the amount of area we use for collection of solar energy. Okay, so here in China you can see how much area they have used for collection of solar thermal, and then you can see other, and then in India we are also not bad. It's about 15 lakhs, okay, 15 lakhs square meter area is covered by solar thermal. Okay, that's to the 2022 report. But here in the second plot, what you can see, it's a solar thermal installed capacity. It is something like kilowatt thermal per 1000 inhabitants. So since our population is very, very high, so our name is not there in this list. Okay. So it's very, very minimal because of the population, right? And of course, France position is not there in the same plot. So it's quite interesting, right? So you can say like how much thermal energy you have harvested per 1,000 habitant. Okay. And also you must know one thing: if you devise a flat plate collector of area 2 square meter, so you can actually reduce 195 kilogram of carbon dioxide per year. That's quite interesting. Now we'll discuss something about the different modes of exploiting solar energy. Already you are aware it is something like a direct conversion from solar radiation to electricity, this solar PV. Then we can go for some kind of panels, solar hot water systems, and we can generate moderate heat, okay, and that heat can be used for thermal applications. Also we can use for electricity production if we have some kind of device which concentrate the solar radiations, and this is also thermal route. Okay, you just intensify the solar radiations, then you generate heat, then you exchange that heat with that working fluid, and then you use conventional Rankine cycle and then produce electricity, right? So it looks something like this. Mostly this solar flat plate collectors we install over the rooftops, right? And it depends the kind of flat plate collectors we use. It may be flat plate collector, it may be evacuated tube collector, it may be heat pipe collectors. So these are different generations of flat plate collectors. Earlier we had only flat plate collectors. Then what was the concern? We need to enhance the efficiency. So how to enhance the efficiency? So you come to know the different parameters which influences the performance of solar flat plate collector. Okay. So can we increase the transmissivity of the glass? Can we use some kind of selective coatings which increases the absorptivity of solar radiations and reduces the emissivity of the radiations? Can we use some other mechanisms which actually enhances the efficiency? Something like when we use to bond, like pressure bonding is done when we have flat plate collectors and then tubes, then we need to attach somewhere, we need to apply some kind of material there to fix it. So what could be the thermal resistances offered by this foreign material? So can we remove it? So these are the challenges, and that's how like evacuated tube collectors. So what they did, they actually try to reduce the convective heat transfer so that they can maximize the energy conversion, right? So that's how development is there. But one thing it is clear, this has to be installed over the roof space, okay? And here in case of solar PV, that can be over the roof space or maybe in the ground, okay? So you can have solar modules, you need to convert this direct current to the alternating current, then you transmit to your what is called transmitter, and then it transmits power by using other electrical components, okay? Nowadays we have net meter system, so the energy you generate, you can actually know if you are not utilizing, you can give it to the grid, and when you require you can take it from the grid. A net meter will count the amount of energy you have delivered and amount of energy you have consumed, and that way you need to pay the bills, or maybe you can gain the money in terms of selling the electricity, okay? Now we'll spend more time on solar thermal collectors. So what is solar thermal collector? It's a device, right, to collect solar energy and transform it into thermal energy by using heat transfer fluid like water, air, ethylene glycol, or maybe other fluid. Can you tell me at what condition we need to use ethylene glycol? Can someone tell me? And what condition we go for water? You can see water everywhere. Suppose if we suggest this technology in Ladakh or maybe Siachen, this will not work, right? It will freeze. So we need a fluid which will never freeze, right? So that's how glycol is used. So freezing point, you can find out now what is the freezing point of glycol, right? Well, thermal energy systems provide thermal energy for various processes. For cold climates, it is very effective, because in our place we never experience for no heating. We need actually cooling in summer, not heating. Hardly we use heaters, except those who are in staying in high altitude areas, like it is more than maybe 500 meter from the sea level. Okay. But mostly we are below the 500 level, so we don't need that much of heating things, but we need cooling. Okay, that's how we are stressing more on vapor absorption refrigeration system. Can we have a low cost vapor absorption refrigeration system? Can we have a solar assisted dehumidifier? These are a requirement for us. Even in high temperature heating applications, significant amount of fuel can be saved by using solar collector preheating. So these are primary applications across the globe. We can also characterize or classify the flat plate collectors as per this. So it may be concentrating collector or maybe non-concentrating collectors. If it is a flat plate collectors, you are not concentrating the beams, right? So amount of solar radiation falling on your collector and the amount of radiation you are receiving is same. So area is same. So that means your concentration ratio is 1. So if you are increasing the concentration ratio, that means the area you are increasing, area of reflection. So for example, if I say concentrator, solar radiation comes and parabolic concentration, it strikes on the concentrator, then it goes back to the receiver. Okay. So if you now compare to the area of the concentrator, area of the absorber, both are different, right? So it is like area of the concentrator to the area of the absorber. So it is more than 1, right? So that's how we can say that how intense heat will be if we increase the concentration of the system, right? So that's how we can classify concentrating and non-concentrating collectors. Okay, and there are many classes on non-concentrating. It may be flat plate collectors, unglazed collectors. Sometimes we never apply glasses. Maybe in plastics, we can use plastics. Solar radiation can transmit, but it's what will be the transmissivity of the plastic or polythene? What I mean. Or glazing, we have glasses. So what could be the transmissivity? So transmissivity is something like, in technical terms we call it as extinction coefficient. What could be the extinction coefficient of the glass? Then solar air heater, it may be glazed or it may be unglazed. Then evacuated tube collectors, again we can classify these evacuated tube collectors in different categories. It may be water in glass, it may be U-type or it may be heat pipe. Okay. And under concentrating, it may be flat concentrator, and we can have flat plate, but we can give some kind of additional mirrors to reflect the radiation to that collector, so that we can increase the concentration ratio of the system, so that we can make it workable at higher temperature than normal flat plate collector. Then compound parabolic collector, then parabolic trough collectors, we have linear Fresnel, then heliostat, then parabolic disc collectors. Okay. So these are building integrated solar thermal systems, what is called BIST. And sometimes you can see some hybrid systems like concentrating flat concentrator, or it may be compound parabolic collectors. So you can name it, but no basic concept is same. You want solar radiation from the sun and you need to convert it to thermal energy. Okay. Sometimes we can use this technology for electrical energy production as well, but its conversion efficiency is low. Okay. If we work at flat plate collector, suppose you have a flat plate collector, but your demand is to generate electricity, it is also possible, because you have organic fluids which actually which boils at low temperature, and you can generate some vapor, and that is okay for generating some kind of power. But the efficiency of that kind of collector is very less. It is about 5 to 7%. Okay. But in case of parabolic trough or maybe linear Fresnel or maybe heliostat, so you can go up to a temperature of 600 to 700 degrees Celsius. Okay. So it's a very high temperature. So it is something like our conventional organic Rankine cycle. So for informations, the maximum temperature what we can provide to the organic Rankine cycle is 540 degrees Celsius, right? So that kind of efficiency. That means that will lead to an efficiency about 35 to 40%. That is also possible to achieve by using this technology like heliostat field collectors. Now, these are the devices for solar thermal collections. It may be liquid flat plate collector. If your temperature requirement is about 40 to 90 degree, then you can go for this kind of collector. Then evacuated tube, you can go beyond 100. Then solar air heaters, then cylindrical parabolic concentrators if your temperature requirement is up to 400 degrees Celsius. Okay, and then paraboloid concentrating collectors, it can go beyond 400 degrees Celsius. So, it is maybe 600 degrees Celsius. So, there are some of the snapshots of those technologies. So, what you can see at the bottom, it's a central power receiver system. So, you have a pole here, at the top you will have absorber, and along the periphery you will have all the heliostats. So, it is a glass kind. Solar radiation falls, it reflects to the receiver. So, from all sides it comes and receives at the receiver at the top. So, from far what you will see, it is like a milky white substance. It is a very intense heat is generated, right, and then molten salt is actually pumped. It is cold molten and heat exchange will be there, and it's come down and heat exchange with water and produce steam and then produce electricity by using Rankine cycle. So, that is how it works. And the other one, what you see, it's a parabolic trough. So, this is the concentrator and absorber at the center. So, it's a concentrator, something like that, and this is the absorber. Okay, solar radiation comes, strikes, and then reflect to this absorber, and then heat transfer flows through these tubes, and you can collect in the other side, and then you can use it both in thermal as well as electricity generation. And these are thermal applications. You can use it for water heating, space heating applications, maybe power generation, then distillation is quite a good thing. Like, no, you need distilled water. Suppose if you have a solar power plant and you are using batteries, so you need distilled water. So, distilled water can be produced by using this distillation. Your requirement is not that much, so that water you can feed it there, and that will work for the batteries. And more extensively, drying. In the last lecture of mine, I will include something about drying, what interesting things can happen and how we can design a collector for harvesting solar energy. And then cooking. So, there are some of the snapshots of drying, and this is something like a desalination unit. There is a glass cover, solar radiation falls, and then water evaporates. Then, since the temperature of the glass is lower, it condenses and you can collect the dye, and this is distillate actually. And you can see this other arrangement like what is called Schaeffler cooker. It's quite effective in some of the places. Okay, so solar radiation falls, and then you have a cooker at the focal point, and you can heat it and you can cook it. Okay, but these conventional box cookers are not that efficient. But when required, suppose even in desert, middle of the desert, you don't have anything to cook. So, you can carry those box and you can cook food, and it's done. It can be done. Okay. So, we can have concentrating collectors and non-concentrating collectors. So, solar radiation is converted from a large area to a small area using optical means, and this falls under concentrating category. And in concentrating collectors, we need beam radiation. So, we'll see slowly. Once I complete this part, then we'll enter to the radiation. So, what are different radiations we need. So, it's just for your informations, we have two primary classes of radiation. It's normal radiation and diffuse radiation, right. Of course, we have to account sometimes reflected radiations, right. So, these normal radiations are more important in case of concentrating collectors, okay. But both beam radiations and diffuse radiations are applied in case of non-concentrating collectors, okay, because its intensity of diffuse radiation is lower. I will explain by its character. And the diffuse radiation has no unique direction, and so does not obey optical principles, and that is how we cannot concentrate diffuse radiation in a concentrator. Okay. And for concentrating collectors, the primary advantage is we can generate high temperature because of these optical means. Okay. And also we need to mention three important things about this collector. These are called performance indices. One is collector efficiency, then concentration ratio, and then temperature range. Okay. So, collector efficiency can be defined as the ratio of energy actually absorbed and transferred to the heat transfer fluid by collector, and this is nothing but useful heat gain to the amount of radiation incident on the collector. Okay. And concentration ratio, as I said before, can be defined as the ratio of the area of the aperture of the system to the area of the receiver. And this aperture area of the system is projected area of the collector facing the beam. Okay. So, for flat plate collector, concentration ratio is 1 because the area of the concentrator and absorber is same. But in case of line focus system, line focus systems are something like one axis tracking, and the point focus systems are two axis tracking. So, you can actually track the beam radiation, and that is how we can intensify the radiation, and that is how we can generate high temperature. And of course, these concentration ratios are actually related to the temperatures. Now, if we talk about flat plate collector, which is a very simple device, and this does not require any sun tracking, and it cannot do also because it is very heavy, and you cannot use this collector to track. Okay. So, we fix this beta, but this beta is very important. What beta you can see, it's a tilt angle. So, what tilt angle you are going to fix? Because see, this earth and sun, they are related, not always we are exposing to the sun. Okay. So, these values will change, winter will be different and summer it will be different because it is significant, but every day it is different actually. Okay. So, if you count n is different, and that is how we get different values for all the calculations. So, we will spend some time for calculation of beta maybe in the next tutorial, because it plays a very important role. And this flat plate collector can properly secured on a rigid platform, and thus becoming mechanically stronger than those requiring flexibility for tracking purposes. And of course, this kind of collectors are always installed in the field, right. So, it looks something like this. You have the collector, okay, and then tubes will be there, will come in the next discussion, and then it plays at certain angles, and beta is very sensitive to the time and days maybe. That is how what we do, since it is very robust, we cannot have facility to track. So, we fix some beta which is moderate to give a better performance, okay, not the best performance. Okay. This FPC consists of a absorber plate. What is there you can see, this is the absorber plate, okay, and the tube fixed to the absorber plate. These are the tubes. There are different configurations of the tubes. Okay. So, it may be something like this. If we say it may be sometimes something like this. So, what you have seen here, and sometimes what you will see, this is an observer plate, and you will have tubes here, and sometimes your configuration will be something like this. This is the observer plate at the below. Okay. So, different configurations you will have. So, what you can see is this kind. While doing so, actually you can increase the efficiency, because as I said before, this contact resistance. So, something you have to apply here. This is normally pressure bonded. You have some kind of foreign materials to be there, and this actually acts as thermal resistance to the heat flows, right. So, can we remove this? So, this is the configurations by which we can remove it. Okay. Even though these are very tiny, but its impact is very, very high if you talk about thousands and lakhs of square meter areas of flat plate collectors. Okay. Then you have transparent cover, this is the glass cover. Okay. So, how many covers you are going to place over the absorber plate? Is single cover or double cover or triple cover? What will happen if we apply some kind of selective coatings over this absorber plate? So, we will discuss those aspects as well. So, if we see this figure, this is quite interesting. This vertical axis shows about useful power and horizontal axis shows the temperature plate above ambient. So, that is TA, this is plate P, okay, plate temperature. So, solar radiation is falling, that is why it is incident, okay, and this much is absorbed and there will be some losses and finally we will get some kind of collection. So, mathematically we will represent those in the coming slides. And what advantage we are getting here? We are actually utilizing both beam as well as diffuse component of solar radiation, okay, and only very limited maintenance is required, and disadvantage is collection efficiency is low due to the absence of optical concentrator. So, based on our requirement we can select what technology will be best, and of course, we can augment its technology or augment its what is called performance by doing something. Okay. So, this is about the absorber plate. So, normally this material of construction of the absorber plate is copper, also nowadays aluminum is used because its cost, copper is much costlier than aluminum, okay. And thickness is about 0.2 to 0.7 mm. You can see its construction, and tube diameter is about 1 to 1.5 centimeter, and tubes are soldered, then braced or pressure bonded, mostly pressure bonding is done to the bottom of the absorber plate, and pitch, its distance between two tubes is about 5 to 12 centimeters, and some are already there, I explained it. So, here this is the header for cold fluid and this is the header for the high temperature fluid. So, what happens? Cold fluid enters, and since solar radiation is exposed, what happens due to the density difference, fluid will move from lower to upper, and then this is the cold fluid, and we can store the hot fluid, we can store the hot fluid at the end. Okay. So, these diameters headers are somewhat bigger than the tubes, and that is how it is, diameter is 2 to 2.5 centimeter. And absorber plate is there to maximize the solar radiation incident on the plate. Okay. So, how to maximize the solar radiations? That's the challenge. Can we make some kind of selective coatings? Of course, selective coatings are now costly. So, this is something like one kind of plastering you can just place over the plate, and that will increase the efficiency of the systems. And of course, how to minimize the losses is the primary things. What mechanism we can apply and what are the materials we can use to maximize it and reduce the heat losses, and how to transfer the heat as fast as possible. So, this cover system is, it looks a single item. So, you see this glass cover, it's not a single line actually, even though it's a, I am taking this glass cover, only one glass cover, there are two glass covers are present here. So, I am taking this one, I do not know what is it. So, I am enlarging this, it is something like this, okay. This part I am enlarging, small one. So, it's actually it is something like this, okay, and complex things happens here. Solar radiation comes, suppose some amount of solar radiation is falling on the glass cover, this is a glass cover, its thickness, this is a thickness, okay. It, some are reflecting, okay, and then we will have it goes internally, it reflects, it goes something like this, it happens something like this, okay, and then so finally you will get something, some kind of radiation here. So this cover system is something like this single cover, but it has got some thickness, and what happens inside this, that's what as you're presenting, right. So that's how we need a very transparent, because normally these glasses are represented in terms of extinction coefficient. So it is, if we increase the transmissivity, so this value of extinction coefficient actually varies from 19 to 4, okay, and it's a K and it's a meter inverse, okay. So if we reduce the extinction coefficient from 19 to 4, then you can actually increase the transmissivity from 0.95 to actually 0.97, okay. That impact is also very, very high, even though it looks very tiny, but impact is very, very high, okay. And this cover is opaque to the long wave radiation, okay, and this is a toughened glass, and normally its thickness is 4 to 5 mm, and so that it should able to absorb some kind of thermal shocks, okay. And normally these gaps between this cover and the absorber plate is about 1.5 to 3 centimeter, okay. And sometimes it is also seen that plastic transparent sheets are also used, but its efficiency is somewhat lower, okay. And of course it is originated from fossil based plants, so we don't encourage this kind of systems to be there. We need insulation and collection boxes, like bottom and sides are usually insulated by mineral wool, rock wool or glass wool. These are insulators. What could be the conductivity of this kind of insulators? It's like 0.03 watt meter Kelvin, right. So that range, it's very, very low thermal conductivity, and thickness about 2.5 to 8 centimeter, and whole assembly is contained within a box which is tilted at a suitable angle. So tilt angle, normally if your requirements, say for example you are devising a flat plate collector for a place like Meghalaya, maybe Shillong, or a place like Gujarat, or a place like Paris, okay, then what could be your concern? First thing, for which purpose you are installing. Say for example, if you talk about say Paris, you are designing this flat plate collector. So your target should be why you are installing this, because in winter you are going to get some kind of thermal energy, okay. So that means what you will do, say for example you start with November or December and then end with maybe March. So during that time you are going to operate it. During that time you optimize what beta maximum or beta optimum for maximum energy, okay. Otherwise if you design beta for maybe June, July, August, that might not work for a place like Paris during the winter, okay. That's just the logic, okay. We'll solve some problem, and that is quite interesting. Then this entire collector box is usually made of aluminum with an epoxy coating on the outside for protections, and face area of the collector is normally 2 square meter. And this kind of configurations, as I already said, are available. Now this is a very interesting problems, okay. So if I talk about, it's a 100 liter capacity thermosiphon, because of this temperature difference there is a fluid flow, and we are not using any passive mechanism to flow the fluid, and solar radiation is 5.5 kilowatt hour per meter square per day, okay. It's daily. Then collector efficiency is 52, then absorber area is given, water inlet temperature is given, then specific heat is given, geyser. So we have a geyser and then solar flat plate collector. We'd like to replace this geyser by flat plate collector. Then what benefit you will get? How are you going to solve this problem? So it's very easy, right? So it is something like is MCPDT. So it is 5.5 kilowatt hour. That means we can get 3600 this kilowatt second, okay, and multiplied by area is 2 is the collector area. Then what is the efficiency? Efficiency is about 0.52, okay, which is equal to mCp dt. So what is m here? 100 liter is 100 kg. It's clear? 100 liter is 100 kg because density is 1000 kg per cubic meter, right? So from that we can say it is 100 liter is 100 kg. So it is 1000 m, then Cp is 4.18. Then you will have delta T is to be calculated. So if you have calculator, you can find out what is delta T, okay. Once you know delta T, then what you can find out what is the outlet temperature. Then outlet temperature will be this delta T plus T1. T1 is your ambient temperature is 23. This part is your 23 degrees Celsius, right. So if you calculate, so T2 what you will get is close to 72 degrees Celsius, okay. So this T2 will be 72 degrees Celsius closely, okay. So again, once you know this geyser efficiency and also you know the solar radiation, this is 5.5 multiplied by what you will have is 2 and an efficiency is 0.52 and its geyser efficiency is 0.96. So this will give you the daily energy, say, because this 5.5 is daily energy, okay. So if you calculate, you can find out a value, you can tell me what value you will get here, and this will be per day energy savings. So if you multiply with 30, then what you will get is a monthly average values. So I have done the calculations, and it is about 35.7 rupees. It is 35.7, this is Indian rupees per day, okay. So if you need for 1 month, you need to multiply with 30. So it is about 1000 rupees, right. So it's a significant save. In 1 year, you will get 12,000, close to 12,000. So that's a really, you know, interesting saving. And payback period maybe 2 years you are going to get it. So this is quite practical, and you can find out these parameters. And also you can verify. So there is search already people have prepared. So how this will behave. Sometimes if you don't know anything, but you want the solution, what kind of technology you are going to use to utilize if you have a temperature of 400 degrees Celsius. So you just go and there you see where is a cross section, then you can find out what the efficiency and what are technology you can use it, okay. It's a very user guide for choosing a right collector at right temperature. Also now, this is quite interesting. So what really we are interested at the end, the amount of heat you are going to collect, that is useful heat gain. This is QU. So as I said before, if you could reduce this QL, okay, and also here you can increase, then you can actually gain more, okay. Now our attempt is to find out what is S and what is QL, because this is known to us. Then we can find out what is useful heat gain, right. So this S, even though it looks only S, it's not so simple. Actually it has lot of components, right. So this S is nothing but the incident solar flux absorbed in the absorber. So this is not something like I, because you have glass cover, then you have absorber plate, right. Then you will have all those tubes, and then you will have all insulations. So these all are insulations, okay. So I am talking about this S here, amount of solar radiation absorbed in the absorber, and this IT is the total amount of radiation which is falling on the glass cover, okay. So this S is also a function of IT, okay. So slowly you learn this flux incident on the top cover is something like IB, RB. IB stands for beam radiation, RB stands for it's a parameter, like what way your system is placed, it is at certain angles with respect to the horizontal surfaces. Okay, it's a tilt. Okay, so this is diffuse radiation. This is that coefficient term plus IDRB plus RR. Okay, this is reflected radiations. Okay, this is for diffuse radiations. So this flux which is absorbed in the observer plate has got this kind of expression. So now what you need, of course you can find out this IB by using a device called pyroheliometer, okay, and then ID by pyranometer. So these values can be found out, and we have appropriate mathematical expression for finding out these RB values. I will tell in the coming slides. And problem is with this tau and alpha for beam radiation and tau and alpha for diffuse radiations. So how to find these values? So now let us see how we can find it. And this term tau alpha beam, which is the transmissivity absorptivity product for beam radiation falling on the collector, and this is for diffuse radiation. Now for transmissivity of the covert systems, we want this tau, and then this tau is a function of tau R and tau A. Now we are entering somewhat in complex system. Okay, this tau R is transmissivity obtained by considering only reflection and refraction, and tau A is transmissivity obtained by considering only absorption. Okay. Also we have beam and diffuse radiations. So both the things need to be treated differently. For finding out tau R, we need to analyze this Snell's law. Okay, it is transmissivity based on the reflection, refraction, and Bogart's law is a transmissivity based on absorption. Okay, and then we will go for diffuse radiation. So what condition we can use it for diffuse radiation, that also we will study. Now if we see this Snell's law, if you have an incident beam radiation, if theta 1 is the angle of reflection, incident sorry, and theta 2 is the theta 1 is also the angle of reflection, and refraction is theta 2. So this angle of reflection or refractions can be related with these expressions. Sin theta 1 by sin theta 2 is equal to n2 by n1 if they are of different mediums, right. This is the refractive indices, right, and this is also related with the rho, which is nothing but reflectivity of two component of polarization. Okay, it's a light, it's a polarization. So it's a polarization. Both sides it happens. It's something like this and other side. And the two components of polarizations we need to take care. This is represented something. We are not going to derive these expressions. We need to consider. We have to stop somewhere. Okay, so these are the two expressions. And for normal incidence, theta 1 will be 0, and we will have this expression. Okay. Similarly, we can go for transmitted tau R expressions, and we can find out tau R by averaging this two component of polarization of transmissivities, tau R1 and tau R2. Okay. So once you are done with this tau R, then we can go for tau A. Okay. And for this, as I explained before, so radiation comes here, it goes back and transmitted, again it reflects internally, and then some of the radiation goes out. So what really we want, this is the sum. This much actually contributing to the heat effect, right? And that's how this is the infinite series, and we can sum it, and finally for n number of coverts we can develop the mathematical expression for tau R1 and tau R2, because you don't know how many covers are required to optimize the performance. Okay, so that's how we can get the expression. So M stands for number of covers. Now we'll go for transmissivity based on absorption, and this is obtained by assuming that attenuation due to absorption is proportional to the local intensity. Okay, so this Bogart's law says di is equal to minus ki dx. Okay, so if you take like di by di minus kx and integrate, because this is the cover system. Okay, this is a single cover you see one line, but this is expanded thing, right. So delta C is the thickness of that cover, and then we have taken a small segment out of that, and this is the radiation takes place, and that's how 0 to delta C is the integration. So if you do the integration, then what are you going to get is tau A e to the power of minus k delta C, and this k is nothing but extinction coefficient. Okay, so its dimension is sure. So it's meter inverse, okay, for glass, and yeah. So that's how we can get this tower. So if you do the integration, and then it will be tau A to the power of k delta C, considering that it is falling normally. So if this radiation entered at certain angles, then what will happen? So that condition also I have reported. So when the beam is incident at an angle of theta 1, okay, with the normal to the horizontal surface, the path travel through the cover would be delta C by. So you can immediately find out what could be this theta, because this theta 1, theta 2, and then if you take AB cos beta, it will be delta C, and from that you can find out what is AB. Okay. So if this is the case, then you can do the integration and you can find out finally what is the expression for tau A e to the power of minus k delta C by cos of theta 2. So if you know this theta 2, then you can find out what is the tau A. Okay. So that means you know tau R, how to calculate, you know tau A, so then you can find out what is tau, right. So it's very easy now. So that's how we can I have formulated a problem, it is solved problem. I'll show you in the next slide. So now that is done for tau. So what will happen tau for beam radiation? What will happen for diffuse radiation? That's the concern now. So what will happen for diffuse radiation? This diffuse radiation is equivalent to the beam radiation coming at an angle of 60 degree. Okay. So this angle is arrived at by considering the variation of transmissivity and by assuming that the amount of diffuse radiation coming from all the direction is same. Okay. So let us take a example. So we are going to plot the variation of tau R, tau A and tau. That is the example. So material we are considering glass, and number of cover we are using 2 covers. So glass cover 1, glass cover 2, then we have absorber plate, and then you have tubes and other things. Then thickness of each cover is 4 mm. Reflective indices are given, relative to air is 1.52, and extinction coefficient of the glass is 15 meter inverse. Okay. We need to find out all values, and we need to generate this kind of plot. Actually, you will get this kind of plot. That's why in 60, the radiation what is coming at 60 is equivalent to like diffuse radiation. Okay. So now this is the calculations I have done. So what is rho 1? What is rho 2, and then tau R1, tau R2, okay, and then finally you find out what is tau R, because tau R is the important thing we need to find out, and then we need to find out what is tau, okay, and for that actually we need to find theta 2 as well. So we can actually take different angles. Just I have shown only one what is called angle at 30 degree. You can consider at 15, 30, 45, 60, then 90. Okay. Then you see what kind of plot you will get. So it will be something like what I have shown. This kind of plot you will get. Okay. So all are converged at 90. Okay. It will be at 0, right, at 90. So this kind of plots you can generate. So if you are very excited to see, really you can do it. It's very easy. So you can take a snapshot and you can do the calculations for other angles. Maybe a spreadsheet you can use and then do the calculations anywhere you can generate the plot. Okay. So these are very important aspects, and this is really important if you can correlate with the performance of the system. Okay. And also sometimes this product we call it as transmissivity absorptivity product is very significant, that is defines as the ratio of the flux absorbed in the absorber plate to the flux incident on the cover system. Okay. So radiation falls, this is the cover, this is now absorber plate, this is now absorber plate, and this is your cover system, right. So now cover system is only single line. Earlier what happened, you have expanded it, it is like a single line now. So this is transmitted, and then again it goes to the tube. So these are like, it is going to the tube after absorber plate, right. So that's how this is very, very important. And net fraction of it is absorbed, it's an infinite series, you can sum it, and if you sum it, then you will get this expression, right. So for diffused, this is diffuse reflectivity of the covert system, it is 0.21 for two covert systems and 0.15 for single covert system, okay. And this rho d can be found by determining the values of tau a 1 minus tau r for the covert system for incident at an angle of 60 degree. So that means we know all the parameters now. So for diffuse as well as beam radiation or direct radiation, right. So this is the very important informations, and also you must remember what is S now. So what happens, we have done this tau a, tau alpha for beam, tau alpha for diffuse radiation, then we can find out S, because already we have calculated the IB and ID by using those instruments, or if you do not have the instruments, of course we have to use for some kind of correlations, right. And this RBR is mathematical expressions, we can use those expressions and we can find out those values. So that means we can now calculate what is S, okay. So once we know S, then what is next, we need to find out is QL, this losses, okay. This is very, very important. Right now you can play the game, that means if you increase or decrease the transmissivity, then what will happen, okay. As I said, is transmissivity, if you can increase, okay, that means extinction coefficient from 19 to 4, actually we can increase the transmissivity from 0.95 to 0.97. That is really impactful result you can get if you do this. Now we will calculate the losses, okay. Then we can find out what is the amount of useful energy you gain. So energy balance if we make on the absorber plate, this is the absorber plate now, solar radiation is falling, and this is the top losses, side losses and bottom losses. So this is the plate temperature. Normally this temperature is unknown and it is very difficult to know. It is inside, you need to have a lot of thermocouples, and this is non homogeneous, okay. It's really very, very complex, but there are some expressions to find out this QU in terms of fluid inlet temperature. That is called Hotel-Wheel-Bliss equations, Wheeler-Bliss equation. So that equation we use to find out this QU, but for your understanding you must know how this can be calculated, okay. So this S is known because already this part we have done. Now our things is QL. So once you know now this one, then immediately you can find out what is QU, okay. So this heat loss from the collector can be mathematically expressed as UL APT PM minus TA. TPM is the plate mean temperature and A is the ambient, TA is the ambient temperature, and UL is the overall loss coefficient, okay. And this QL actually sum of all the losses, it may be from top, it may be from sides, it may be from bottoms, okay. That is how we can say this heat loss from the collector is the sum of heat loss from the top, bottom and sides, and mathematically we can represent something like this. And this can also be expressed in terms of loss coefficients, okay. So this, how this can be expressed in loss coefficients, rate at which heat is lost from the top is something like this, UT, then this for UB is for bottom and US from the sides, and these all are constant now, and this is also constant, we are considering constant. So if we sum it, it will be something like this, okay, because these are constant, so this will go each other, and finally also we can find out the loss coefficient will be your UL is UT plus UB plus US, okay. So now if you know these losses, then you can find out what could be your QU, and also you can give a check. If this value falls between 2 and 10 watt meter square Kelvin, then your design is okay, and if it is very close to 2, then you can say you have done a very good design, and if it is more than that, no, your design is somewhat not good, okay. So this is a set point, like no, okay, this value is in between, then you are done, because you need to do lot of calculations. I will show in the tutorial part. And these losses can also be drawn, like you have studied in heat transfer, like once you have a slab, and then you can consider it like a resistance, like it's like a Ohm's law, analogous to the Ohm's law. It's temperature difference and potential difference, and current flows and heat flows. Okay, so it's analogous to the Ohm's law, or Ohm's law is analogous to our thermal resistance. Okay, so that's how we can write something like this from TPM to ambient. It is from sides, from bottom, and this is from top. Okay, and this can be again redrawn to represent equivalent the resistance network. It represented something like this. Okay, it take care of all the losses, okay, what we have represented in the last slide. So now we will represent the situation to know or to estimate the top loss coefficient if we consider two cover system and a plate. Okay. So what happens, solar radiation comes and strikes on the observer plate, and then it goes up. Okay. We will also explain how radiation propagates from sun to the earth surface very clearly. Okay. But here in this case, what happens, solar radiation comes and strikes on this glass plate, and then it goes up. That means what we can say, this TPM is more than TC1 and TC1 is more than TC2. Then you have a T sky. Okay. What is T sky temperature? Do you have any idea? What is the difference between ambient temperature and sky temperature? So sky temperature is something like when solar radiation comes, okay, what happens, these emissions or radiations are trapped in the gas molecules, and that emits the radiation, because any objects having temperature more than absolute 0 will emit thermal radiation. So that actually retains heat and it emits radiation, and radiation exchange takes place from one object to another object. It is not ambient temperature, actually it is exchanging heat from the glass cover to the object, that is like gas. Okay. So this is like T sky. That is why when we write very precise mathematical expression for radiation by using Stephen Boltzmann's law, we write always T sky, not the ambient temperature. Okay. So ambient temperature is for convection, not for radiation. Okay. So that is how what we can say here, but you must remember one strategy, this TPM is always greater than TC1, is always greater than TC2, and TC2 is always greater than T sky. So this actually help you or guide you to solve some of the important problems which I am going to study in the next tutorial section. So we will have this heat exchange from plate to glass cover 1, then from glass cover 1 to glass cover 2, then glass cover 2 to ambient. Okay. So this has been something like this. So from top to QT divided by AP is HPC1, this is P to C1, TPM minus TC1, and then there will be radiation exchange between the plates, this plate and glass cover. That is how, and this is radiation parameters, because how these plates are view each other. If they are in parallel, then we can use this expression. Okay. If it is enclosed surface, their expression will be different. If it is spherical, then things will be different. Okay. So since these plates are parallel to each other, then we can use this expression, right? It is a radiation parameter or view factor, you can say. This P is for plate and this is for collector. Okay. And these are unknown. We need to know what is called assume those values. And then from first cover to the second cover, distinction, second cover, third cover, but this has to be same for all. This expression 1, if you say this is 1, this is 2, this is 3, this QTAP has to be same for all. Okay. So that you should remember. When you are solving these expressions, suppose if you consider any temperature and solve it, if you found different values, then your choice is not perfect. Then you need to redo the calculations until and unless you get a very close value of Qt by AP for all the expressions. Okay. And for this kind of situations, I am not giving a lot of correlations, heat transfer correlations for finding out this heat transfer coefficient, because from glass cover, from plate to the glass cover 1, these are all parallel, and you need to find out what is Ra cos beta. It's a Rayleigh's number multiplied by cos of beta at what angle it is located, this tilt. Okay. So if the range is in between these two values, then you will use this, and if it is in these two values, then you will use this expression, and then similarly in the last expression. Okay. But this properties to be evaluated at the arithmetic mean of the surface temperature, because mean temperature. So this glass cover 1, and this is maybe plate, and this glass cover 2, right. So here you know this temperature, say for example this is TPM and this is TC1. So what happens, this is air, okay, this air temperature is different, right. So what you need to find out, what could be the properties of air at this portion, it will give you at a temperature of TPM plus TC1 divided by 2. At this temperature normally we take the properties of air, then you can do the calculations for heat transfer, and this expression, this correlations will give you heat transfer coefficient, because this Nusselt number is H, and this is characteristic length will be your this length, okay, not the diameter here, and not this way, this is the way heat is exchanging. Okay. So which way heat is exchanging? Of course it is from observer plate to the glass cover in the vertically up. Okay. So that's how it is L, okay, HL by K, that direction, because heat is flowing from this direction, and that's how we should consider L here. Okay. That means thickness, and then you can find that what is H plate to C1 one case, and other case it's C1 to C2, and then accordingly you can find out no other heat transfer coefficient. Okay. So we can also use these correlations for finding out HW. HW, what is HW? If you go back, this is HW. So when we have heat exchange from TC to the ambient, then we need to use this HW, right. So this HW already correlated by many researchers. So that's how we can find out this HW is 5.7 plus 3.8 into U. U is the velocity of wind, or at what velocity particles are moving there. Okay. If you know that, then you can find out, and either of the correlations can be used. And as I said, this T sky and TA are related. Macadams, they have correlated that this T sky is about 6 degrees lesser than ambient. It is TA minus 6. Okay. So that's how we can take this sky temperature is TA minus 6. And once that is done, that's for top. So now we need to find out for bottom and sides. So for sides, if you know this conductivity, so thickness and conductivity of the insulations, then you can find out what is the bottom loss coefficient, and this is by considering convection losses from absorber plate towards the downward direction. Okay. Its bottom loss coefficient can be find out according to this expression. And for side loss coefficients, because there are many sides, okay, you have these two sides and 4 sides you have of different dimensions. Two of the dimensions are same, and that's how we can get this area, and we can do this is as a mathematical calculations, and we can find out what is US if you know the dimension of the collector. Okay. So this is dimension, this is L1 and this is L2, and you know the temperature difference here. Okay. So this US can be calculated. That means you know now what is UT, what is UB, and what is US. That means you know now what is UL. That means you have started with something like QU. So you need to know this QU, and then this term, that energy what is absorbed minus QL, and this QL is nothing but function of all these losses. So you know all the parameters now. then you can find out what is QU. So that is done. Okay, that's how we can design a flat plate collector. Okay, now also we need to discuss two very important parameters. You are confident that you know this expression and QL, then you can find out what is QU. Now we are going to calculate this instantaneous collector efficiency. What could be the collector efficiency? Okay. So this collector efficiency, or normally in solar calculations we consider 1 hour is instantaneous, not in 1 second. Okay. So because we consider that in 1 hour this radiation is not going to very much. So that's why we consider 1 hour time is instantaneous time. So this is useful heat gain to the radiation incident on the collector. It is QU by AC IT. Okay. Thus AC is the collector area and IT is the total radiation which is falling on the collector, and QU is the useful heat gain, right. Now you also need to know this AC and what is the relationship between AC and AP. AC is the collector gross area and AP is the plate area. Okay. So this AC is something like about 15 to 20 times more than AP. Okay. That's how we consider 1.2 times more than AP most of the cases. Now we are going to select the material. Which material will be selected for your application? What is the basis of selection? You must know up to what temperature your system will work. That's the first thing, right. So in order to study that, what we do, normally we study a temperature called stagnation temperature. That's the maximum temperature a solar flat plate collector can provide. Okay. So how do you understand that? You fix it in a particular place, that flat plate collector, and don't take the heat out from the system from morning to the evening, maybe at 4 o'clock, and you see what temperature you will get at 4 o'clock, and that is nothing but your maximum temperature or stagnation temperature when you are not utilizing the heat. That means QU is 0, right. So if QU is 0, then what happens? So you know expression for this, then QU is 0 means loss QL is be APS. This is the condition at which you will get the maximum temperature, and this temperature is very, very important for designing a solar collector. Okay. So that's how I said is useful as an indicator for comparing the different collector design. Okay. And it is useful for construction of a collector. So these 2 points you should always remember as far as collector design is concerned. Okay. Now we know how to evaluate. Now more complex things will come now. Okay. So this is just an example. So if I go provide this top loss coefficient, because investigating top loss coefficient is more complex, and I am giving this value, and immediately you can find out other values. If I know the thickness and then insulation and then size of the collector, then we can find out what is US, and finally you can find out what is UL, and that takes about 7.57, which is less than 20 watt meter square per degree Celsius. That means it is well designed. Now so far the expressions what we got is QU in terms of TPM, plate mean temperature. Okay. So which is very, very difficult to find. So we need an expression which will give you QU in terms of fluid inlet temperature. So how to do that? So in order to do that, so we need to analyze two important parameters. One is called collector efficiency factor and other one is collector heat removal factor. Okay. So you got this information already, you are aware about it. If you have two glass cover and then one absorber system, right? And also we can draw this kind of thermal resistance. Okay. For if you are doing very microscopic analysis, then this will be something like this. Okay. So this is the temperature profile. What happens? This is your absorber plate and you have attached these tubes. So heat transfer fluid is flowing through these tubes. So what happens inside? So this will be fixed at constant temperature, and then there will be rise, and then this will be something like this, and your tube is here and this tube is here. That means it's not so, it will gradually it will go something like this. Okay. So in between there will be temperature rise. So it is something like this is x, that's why I say this is x, and along the length it is y. Okay. So along the x your variation will be something like this, and along the y, suppose if you consider this tube, so this is at TFI, fluid inlet temperature, and outside what will go out is TFO. Okay. So if we take a plot in a y direction, so it will be something like this. Okay. So temperature, inlet temperature will vary from inlet to outlet, but in between the tubes you will have this kind of temperature profile, right. So now we consider a small segment and do the analysis and see how this can be calculated. So these are the expressions. First let us define what is collector efficiency factor and heat removal factor, and why we are doing this. So why we are doing this? Because we would like to establish a relationship of something like this. So TFI. So earlier QU was in terms of TPM, which is very difficult to know. Okay. So this TFI we need to know, always we know like TFI inlet fluid temperature is like ambient temperature. This is known. So it is very easy for us to calculate, but what is FR? So collector heat removal factor is defined as the ratio of actual useful heat collection rate to the useful heat collection rate which would occur if the collector absorber plate are at the temperature of TFI everywhere, and its value is 0 to 1. Okay. So higher the value, better is the good, better is the performance. Okay. Okay. And also we can actually define this FR. It's we can actually derive the entire things, and something I will derive, and but I am not going to solve it here, but I will just show you the mathematical expression how this can be done. Okay. And the collector heat removal factor is similarly, but this we are maintaining at the temperature of TF, and it values varies from 0.8 to 0.95. Okay. But you must know why we are doing this. Okay. So that's how we can consider a one dimensional flow of heat in the absorber plate in the direction of at the right angles to the direction of the heat fluid flows, and heat flow from the plate to the fluid across the wall, and one dimensional flow of fluid inside the tube. Okay. So these are the considerations for our calculations, and then if we take a small segment, this is the segment, this is in between the tubes, and dy is the other side perpendicular to the board, and then we can do the energy balance and see what happens. So you can get this kind of expression. I will share those documents, you can just read it, that is not a big thing. Just we have considered one single element and apply the energy balance, and finally we got an expression of something like this, and we'll just show the final results, and this is in between you will get these results. I think I missed one thing. Okay, this is for n number of tubes, and we can do it. Okay, okay. Later on we'll get the expression. So for collector efficiency factor, what advantage you get? So here this is the absorber plate, and you have applied or you have given some foreign material inside whose thermal conductivity is different than the material here and here. Okay. So you need to consider the thermal resistance offered by that material. Okay. So if we make a single material, then it's always good, then we can actually discard that thermal resistance offered by that material. That's the one novel collector systems you can thought of. And for our analysis, what we did know, this tube wall resistance offered by the tube wall we have not considered, and we have done the analysis, and see what we will get at the end. We will get an expression of something like this if configuration is something like this. Just below we have attached this tube, then QE will be at this APS. This APS is nothing but collector efficiency factor, and this expressions you will get, and this is in TF. Okay. And for different configurations you will have different this. So, here you can see inline we will actually consider, we will discard this losses what is available in case of tube bonded above the absorber plates. Okay. So, that is how this is not there, one portion is not there, this part is not here, delta by this part is not here. So, that is how we can get some kind of higher efficiency in this configuration. So, collector heat renewable factor I can get. So, these are some of the calculations you can see, because we will we cannot discuss all these aspects here, but I will give the informations, you can just do the analysis, and finally what you will get is sorry, this one FR and QU. So, QU what you get, FR APS minus UL TFI minus TA, and this FR is something like this. And what is the significance of this? This is a design parameter, since it is a measure of the thermal resistance encountered by the absorbed solar radiation in reaching the collector fluid. So, it is like one kind of design parameter. Okay. So, lower the value of FR then higher is the efficiency, right. So, how we can do it, that is our concern. Okay. So, then once you can calculate this FR, then you can actually find out what is QU, because all the parameters are known to us. We do not have to think about TPM, it is TFI. So, why this TPM is so interesting, when you solve this problem in the coming slides, then you realize. But you must know what is FR and what is the physical significance of FR. And once you know these other parameters, then we can find out instantaneous efficiency, and throughout the day what is the efficiency. So, it is very easy now, all the parameters are known. And sometimes, since we need to find S, so it is very difficult to find RB, RR and individual IB. So, what we do, we just know this IT and then we multiply with tau alpha average. So, tau alpha average will take care of both beam and diffuse radiation, that is easy for us to calculate. Okay, this is an example. So, this shows an FPC has an aluminum absorber plate, and Kp is given and thickness is given, an area of 1.5 square meter, and it has two riser tubes, each of diameter 0.025 meter, and length of the tube is given to you. We need to determine the collector efficiency factor at this for this collector if the convective heat transfer coefficient from the inner tube surface to the water is 50, 100 and 200 watt meter square degree Celsius, and overall heat transfer coefficient is given. If you do this, then for different cases you can have different values of this, and from these calculations what information you can actually take. So, as you go on increasing this H value, you can actually increase this have these values. Okay. So, what does it mean, like if H value means what? Heat transfer coefficient, heat transfer coefficient more, that means you need to spend more energy to increase the heat transfer coefficient than from passive to active. Okay. So, in expense of some amount of energy, you can actually augment the efficiency of the system. And also you can see, so now similar calculations, but what I said, I change the material from copper to galvanized iron, see what will happen. So, these all are very, very practical, because you are going to build, you are going to design a system. What will happen if you change the material? What will happen if you have different convective coefficients, or maybe heat transfer coefficient? Okay. So, these are all are design aspects. So, you can find out what is add this for this situation. Okay. And also these flat plate collectors can be connected in series, parallel and mixed. Suppose if you stay in a hostel of say capacity 1000, okay, and then if I ask you to design a flat plate collector, then how you will design? What is the design basis? Okay. First, what you need to do, you need to know the amount of heat to be given and then at what temperature. Okay. So, you see like these FPCs are connected to increase the volume of water to be heated. So, if first series means what, its parallel means what, one after another, right. There is a header and at the top you have a header. Then what happens, all are at same temperature, all are at same temperature because they are in parallel. Series means what, so you feed it here and then you take out, and that inlet will be inlet, no, outlet will be inlet to the other, and then you take out, and that outlet will be inlet to the others. So, that is the series connection, right. So, in parallel connections we are promoting to increase the volume of the water, okay. But in case of series connection, what happens, outlet of one row of FPCs is connected to the inlet of the second one of FPCs, and that way it will go on. And while doing so, what happens, mass flow rates are same for all, and the outlet temperature actually increases, okay. So, in series connections you are increasing the outlet temperature, in parallel you are increasing the mass flow, right. Now, if you need to meet the demand for 1000 students in a hostel, then what could be your design basis? So, you see this first FPCs are to connect in the parallel for given capacity of hot water to make one row. How much do you need is quantity, okay, in parallel first, then you make it series, then maybe you can see parallel, then that way you need to design, okay. First you make the arrangement for requirement, then you go for doing this. So, this is very interesting. So, then modules are connected in series to increase the temperature as per the requirement. And you must know this FPCs of this mixed mode will operate in force mode only. That means, you need to spend some kind of pumping power, okay. You need to spend some amount of energy, right. So, this is interesting again as far as design of FPCs are concerned. Now, you see the configurations of parallel plates. So, this is water in header, and this is hot headers, and outlet, from outlet you can store energy, right. And this is like mixed or combined FPCs, okay. So, these are connected in parallel, then it is series, okay. Then you just go on doing it based on your requirement, because in a single system you cannot do it. You have different lobbies and different terrain. So, you just use the particular terrain for a particular set of people, and then you design for other people's, because at a time if you connect, then it will be some of the operational difficulties you might arise while designing. So, this is one way of designing a flat plate collector. Now, what are the parameters it influences the performance? It is like design parameters, then we have operational parameters, meteorological parameters, then environmental parameters, right. So, some of the prominent parameters includes selective surfaces, number of covers, cover tilt, transmissivity, inlet temperature, dust on the top cover, spacing and shading. These are the important parameters. These are also falls under design parameters. Selective surfaces, it is very interesting material. Still, if you see in the Google or maybe Science Direct, you will get a lot of papers on these selective surfaces, because it's a some kind of layers you are laying over a observer plate, and you are increasing the efficiency of the system, okay. So, observer plate surface which exhibit the characteristics of high value of absorptivity for incoming solar radiation and the low value of emissivity for outgoing radiation, okay. So, these characteristics must have. Also, you see, if a surface that has a high absorptivity for wavelength less than 4 microns and a low emissivity of wavelength greater than 4 microns can be prepared, it would have the characteristics of desirable for an observer plate surface to act in the selective fashion, okay. And there are different methods of making it. So, but you see this is very, very thin, it is like about 1 micron is the thickness. So, one of the commercially available selective coating is Sarmens, and it consists of fine metal particles in dielectric or ceramic matrix or a porous oxide impregnated with metals. Okay. And thin film of those composites are transparent in the high wavelength region and strongly absorbing in the solar radiation region. Thus, they may be or they form a stable surface when deposited on the highly reflecting metal surfaces. Okay. And you can see this absorptivity you can increase from 0.8 to 0.99, and then emissivities can be reduced in these cases. So, now you can see some comparison. Hope it is not boring, right? Everything is all right? Yeah. Okay, let me drink water. So, we will finish it. Once it is done, then radiation we will take and then we will finish it. So, selective surfaces, if we talk about this selective surface, non-selective surfaces. Okay. So, first case we have considered absorptivity 0.94 and emissivity 0.14. You can see the efficiency is 43.6. Then there is no selective surface, efficiency is 31.5, and then selective surface with enhancement of absorptivity and no reduction of emissivity 45%. So, you can consider 31 to 45% rise, it is really, really significant, right. So, this is one observations. Then we will have selective surface with number of covers. So, this is the selective surface, and then we increase the cover from 1 to 2, then 2 to 3, and you see what happens. Selective surfaces with single cover is having higher efficiency. That means what? We do not need to increase or invest for buying additional seats. Okay. So, this is not required, right. So, this is sufficient. So, selective coating with single cover is fine. Now, you see non-selective surfaces, we have first 1 cover, 2 cover and then 3 cover system. So, what happens, as you see the efficiency, this 31.5 with single cover, 35.2 this second cover, 2 cover, that means, and if we apply 3 covers, then it is 33.4. That means what? It is without selective surface, what we will have? We will have higher percentage of conversion in case of 2 cover system. Okay. So, with selective coating, single cover and high efficiency, without selective coating, 2 covers and efficiency is lower than selective surfaces. So, it is quite effective to have a selective surface. Now, tilt. So, at what tilt? As we have discussed many things about tilt. So, we have got a lot of expressions. So, this is one of the famous expressions which annual insulations, how we can calculate. So, this, even though it looks somewhat complex, but that it is not that complex once you start with the calculations. We will actually go back and we will show how this expression could be arrived. So, this relative annual insulation is the ratio of the annual insulation for given values of phi and beta. Phi is longitude, right? Sorry, longitude, latitude of the place, and then beta is the tilt, and if it is 0 for both the cases, then what could be relative index? Okay. So, for winter, the recommended value of tilt is phi plus 10. Phi is, so you know how to define latitude. So, suppose this is the globe and your equator is here, right, and this is the prime meridian maybe. So, if we consider a place here, okay, and what you do, you take the radial line, you connect the center of the earth and the place, the angle it makes with the projected equatorial line is actually phi. Okay. So this is actually latitude of the location. So you take the place and then connect to the center of the earth and makes an angle with the projection on the equatorial plane. It is phi, right? So if we for winter they consider phi plus 10 or phi plus 15 is fine. For summer phi minus 10 and phi minus 15. So it's significant, right? It's 30 or 20 degree difference. So it impacts a lot. It is very, very crucial to have understanding on it. Okay. So this for finding out this average or monthly average values of energy falling on the collector plates per unit area, then we can use this expression, and this is monthly average altitude angle at noon. Okay. So you can find out this flux which is represented here, and in order to find this we can differentiate this beta and equal to 0 and then find out what is B optimum. Okay. So this B optimum will be something like this. So it depends on this particular habit. We will solve one problem in the next tutorial session, then your things will be clear to you. Okay. Spacing also important, and what spacing is appropriate between this glass cover and absorber plate. So this also plays an important role, and because it's related to heat transfer. So it actually if you take a certain heat transfer coefficient and its temperature and then delta T variation, it will be something like this actually. So this is spacing, So it says about 4 to 8 centimeter is always good to have the spacing, because it's a relation between space. It may be about 1 centimeter, then here it is maybe 8 centimeter, something like that, and this is Nusselt number or heat transfer coefficient. It goes something like this. So normally 4 to 8 is preferred for this kind of configurations. And also for inlet temperature. So as you go on increasing the inlet temperature, actually you are reducing the instantaneous efficiency. What happens actually, decrease in efficiency is because of the higher temperature level at which the collector as a whole operates when the fluid inlet temperature increases. So as a result, this top loss coefficient is increases and instantaneous efficiency decreases. Okay. Then we will have transmissivity. As I said, this impact a lot. So if you can reduce this transmissivity or K value from 19 to 4, you can actually increase the transmissivity very effectively, and that's impact the performance very significantly. Dust is also important. So normally what the kind of discussions we make is like every day we are cleaning the solar module, but it is not possible, right? Every day cleaning the solar module, it's really not possible. So periodic cleaning, maybe twice in a month is also fine. So in order to have good performance. So once you do this, then really you will get a very good performance. Otherwise you need to multiply with some kind of correction factor, because the calculation what you are doing is for always clean. Okay. So correction factor may be 0.9 to 0.99, you can multiply with that. So these are some new development like convective losses, how you can reduce it. Okay. So that's the attempt to reduce the heat losses and to improve the efficiencies. Okay. So I will not spend much time because you are a little bit bored, but I will make you engage in other calculations soon. Okay. So this is like the further development what people have done, like evacuated tube collectors to reduce the convective losses so that you can increase the efficiency. As I said, if you fundamentally correct, then you can do everything. QL, if you can reduce this QL, you can maximize QU. So these are the attempts to reduce this QL. That's how we understood. Okay. So person wise, it is something like it is double wall, like concentrative tube. Okay. So fluid flows inside the heat transfer fluid, and then in between this concentric tube there is evacuation. Nothing is there. That's how you can reduce the heat transfer losses. Okay. And sometimes when we use this heat pipes technology, so I can deviate slightly more from here. So what happens if you see our electronic devices in laptops, you need cooling, right? So for cooling, what are the devices you use? Like chips are there, it cools. So heat pipes. So heat pipes are used in your machines, in your computers, right? So heat sinks are there. So you know how fast you can remove. Okay. Suppose if I have to gift a laptop to Donald Trump, then maybe I could have designed this laptop by using maybe platinum or maybe some gold, okay? Because it is having high thermal conductivity. Okay, it will reduce the heat transfer very quickly, and then he will be very happy. So when it is heated, when quickly it is dissipated to the air, right? So, but it is not possible for everything, right? Every people, like gold may make all those plates where all thermal conductivities are there, like no heat transfer is there. So we need to compromise. So here again we cannot invest very high conductive material. So this is something like, this is tube and vacuum is here, okay, and here it's a selective coating so that we can maximize the solar radiations. And what happens, there's the wicks, and this is evaporator and this is the condenser. Okay, so what happens, heat actually carries from here, your solar radiation is falling, heat generation will be more, and it will carry cold fluid in, hot fluid goes out, and then here heat actually heat transfer takes place, and you can take this heat for utilization, and QE will be here, and series of this kind of things are attached together, and fluid will flow, and you can get the energy out of the system. And now interesting thing will come. I think you will quick now. Okay. So solar radiation part. So see what is happening. This is a hot object and this is a cold wall, and nothing is there inside, it's a vacuum. So what kind of heat transfer will be there? It's a radiation. So any object if you kept at a temperature more than absolute zero, it will emit thermal radiation, right? So that's what it is used. So body has to be more than absolute zero, okay, and bulk of thermal energy emitted by a body lies in the wavelength between 0.1 to 100 micron. That you must always remember. Thermal radiation, range is 0.1 to 100 micron. Okay, so solar radiation also falls in that range. So that energy transfer from the sun to the earth is by radiation. Okay. See, there are two principles. One is Maxwell's electromagnetic theory, and the second one is Max Planck's constant. Okay. So this Maxwell's electromagnetic theory, radiation is treated as electromagnetic wave, and for Max Planck's concept, this radiation is treated as photons or quanta of energy. Okay. But no such principle is there to explain the radiation spectrum very exhaustively. Okay, that you must know. Okay, and both the concepts are utilized to describe the emission and propagation of radiation. Okay, so result obtained from electromagnetic theory used to predict the radiation properties of the material. Okay, but the result obtained from Planck's concept have been employed to predict the magnitude of radiation energy emitted by a body at a given temperature. So that's how two things are different, but it gives the radiation spectrum of the system. Now you know this thermal radiation, as I said, its wavelength from 0.1 to 100 micron, and solar radiation is 0.1 to 3 microns. Okay, thermal radiation range is very high, right, and solar radiation range is very small. And what is the visible range? Because most of the solar PV systems works on visible range. So this is 0.4 to 0.7 micron. Okay, in that range only this solar cells will work best. Okay, and ultraviolet ray is 0.4 to 10 to the minus 2 micron, and infrared, actually we are interested more on this infrared because we are heat and thermal collectors. Okay, at this moment 0.7 to 1000 micron. Okay, and also you can see how big these radiations are, or say small. Okay, so for building size, humans, radio wave are very high, right? Then microwave, infrared, it's like honeybee, then pinpoint, then you can see like ultraviolet rays and then the gamma rays, these are like no atomic nuclei. Okay, and also you can see this application of those radiations. Gamma rays, it is less than 0.01, then X-rays where it is used, right? Radiologists, people knows it, right? Ultraviolet rays, then visible rays, it's the night vision, infrared, near infrared, then thermal images. You can see the applications already, you know, majority of the applications. Okay. Okay, this angle is 32, and if you convert to degree, it will be 0.53 degree. Okay, and this is one astronomical unit, the distance between sun and earth. Okay, and you know winter solstice and summer solstice. Okay, what is the day? June 22 and then December 22. This is the summer solstice, where declination angle will be minus 23 for 23.45 December 22, and here is a plus 23.45. Okay, this is summer solstice, and for we can say winter equinox and summer equinox. Okay, in the winter equinox is 21, where declination is 0, and summer equinox in September 23, when delta is 0. So here we can say delta is minus 23.45 degree, and this is plus 23.45 degree, and this is 0 degree, and this delta. Okay. So for March and September 0, and then for December and June it is 23.45 in magnitude. Okay. So it always, and our angle, this attains an subtend an angle of 23.5 degree always. This is known to you, right? It's not something like it is at 0 degree, it is rotating. So these informations are required. So solar constant. So if you are there above the earth atmosphere, so our things are something like this. You have earth atmosphere, okay, this may be earth atmosphere, and what is happening here beyond the earth atmosphere, what we call is extraterrestrial region, and inside this what we call is terrestrial region. Okay. So beyond this, what happens, that is not affected by any elements, or maybe what we can say, when solar radiation is coming through this earth atmosphere, what we received is in attenuation form or attenuated form. Okay, that means solar radiations are attenuated by absorption and scattering. Okay, so how this will happen, I will explain soon. But beyond this, it is extraterrestrial region, where ISC is 1367. Okay, but since n is varies, so this also varies. Normally, this intensity of solar radiation in the extraterrestrial region is 1367 watt per meter square. Okay, but it varies because n is varies. So that's why this value is 1367, and extraterrestrial radiation is this, and this actually accounts for different things like its variation. Actual solar radiation flux is plus minus 3.3% variation, because sun earth is not the uniform always. So that variation is about 3.3%, and that actually accounted here 0.003 cos. Okay, so that's how it is related. Okay, and that's how we can see for different times n is the nth day of the year. What is n? So and you can find out, you can substitute, and you can see what is I external, or what is called extraterrestrial region. So now I'll just explain the propagation of solar radiation. So for example, this is the earth surface. Okay, so what happens, solar radiation comes, and actually some are reflected back. Okay, some are actually comes directly to the earth surface. This is the upper layer of the earth atmosphere, and this is the earth surface. Okay, so it comes something like this, and some are diffuse radiations. They don't have specific these are anisotropic, right? There is no specific direction. So what my concern is, so this is Earth atmosphere. So Earth atmosphere composed of different layers, maybe ozone is there, okay, ozone layer already you know. Then you will have H2O will be the water vapor, carbon dioxide will be there, then methane will be there, carbon monoxide will be there, nitrogen will be there, then you have dust or particulate matter, I can say PM, okay. So what happens, you will have scattering will be there. Suppose this is a water vapor, so it will scatter. Is sun. So solar radiations are coming, it's electromagnetic radiation, right? It's a short wave radiation, electromagnetic radiation. So as soon as it comes to the Earth's surface, what happens? Some radiations are reflected back, it's irradiated to the space. Some are goes in, some are goes straightway to the Earth's surface. These are called normal radiation, or I represent it as an IN, is the normal radiation or direct radiation. And what happens? There are water molecules and then other gases. When solar radiations comes, it actually scatter. It actually is directionless. There is no proper direction, and its intensity decreases. What happens actually? One is absorption, ABS. Absorption happens. Other one is scattering. So this absorption happens because of O3 and H2O present in the Earth atmosphere, and scattering happens because of all the gas molecules. You just name it: carbon dioxide, carbon monoxide, nitrogen, then some kind of refrigerants gases, and maybe particulate matter. Because of this, what happens? You will have one more radiations called diffuse radiation, ID. One is for normal radiation or direct radiation, other one is diffuse radiation. Okay, the intensity of diffuse radiation is always lower, right? But contribution of diffuse is also important as far as solar energy conversion is there, right? Now, what technology to be suggested based on the radiation spectrum? That's the concern point. If your normal radiation is far higher, say for example, if you consider a place like Gujarat and Rajasthan, you will have more normal radiation. So in those places, it is very easy to install the solar concentrator as well. Solar PV will anyway work, solar concentrator you can suggest. But a place like Shillong, so you will get mostly diffuse radiation in most of the cases. PV will work, solar thermal will also work to some extent, not that very high, but there is a requirement of exhaustive study in those places to investigate the performance. Okay, you got this idea? So when solar radiations entered in the Earth atmosphere, this will be attenuated due to absorption and scattering. And absorption happens because of O3 and H2O present in the Earth atmosphere, and scattering happens for all the gas molecules presence and particulate matter. Okay, and we are defining two radiations: normal radiation or diffuse radiation, direct radiation, and then diffuse radiation, right? So you will get this kind of spectrum. So here is the dotted line is the extraterrestrial radiation. So extraterrestrial radiation will be something like this, and this part is your like phone কৰি আছো মই টক আছো, and this is for visible range, and this is UV, and this is the infrared part. Okay, when we consider that radiation study beyond the Earth atmosphere, we call it as extraterrestrial radiation, and there radiation are falling normally everywhere. Wherever you stand, you will get the normal radiation on your head. Okay, so that's how we can say it's a AM0. AM0, how do we define? So, suppose this is the radiation travel in the earth atmosphere, primarily we say something like that. So, this if we may consider this is A, this is B and this is C. Okay. So, this AB by BC is equal to cos of theta z. So, this cos theta, now this AM0 implies radiation is in the extraterrestrial region, but when sun ray is on your head in the terrestrial region, then AM is equal to 1. So, if AM is 2, that means your angle is 60. Okay. So, normally solar collectors are tested at an spectrum of AM 1.5, where this angle is 48.8 closely. So, at that angle normally solar modules are tested. So, that is why these spectrums are very, very important. So, AM spectrum, they say when you see the solar panels are coming out or solar modules are coming out, they actually are tested at AM 1.5 always. Okay. That is how this AM air mass, it is AM stands for air mass spectrum 1.5. Okay. So, you can see this like it is a radiation spectrum, and you can see this 44% of the energy is there in the visible ranges and rest is in the near infrared and other wavelength, and UV is about 7%. Okay. So, from here also you can conclude what could be the maximum conversion efficiency of a solar PV module, because 44% energy is there. So, what could be the maximum efficiency? You cannot have 100% efficiency, right. So, only energy what you are getting is 44% energy of the entire spectrum. Okay. So, here what I am showing, it is a sun is a black body, its black body temperature 6000. So, how can you say it is a black body? So, we can actually test it if you know the Planck's law, and then if you integrate this all wavelength from 0 to infinity, then you can find out the Stephen Boltzmann constant. Okay. So, Stephen Boltzmann, EB is sigma to the power of 4. Okay. So, if you substitute the solar constant value and if you try to find out temperature, that temperature is close to actually 6000 degrees Celsius or 6000 Kelvin. Okay. So, then if you take that temperature and vary this wavelength, then you can get the similar spectrum. That is how we can consider it as a black body temperature. Okay. So, say hot sun radiates at shorter wavelength that carry more energy, and the fraction of absorbed by the colder earth is then re-radiated at longer wavelength. So, this is coming from the sun and more amount of energy is carrying by the wavelength which is or radiation coming from the sun, and it is long wave is propagated from the earth surface. Okay. And that is how you can see the maximum wavelength is 10 micron in case of long wave radiation. How much time? Then if someone interested can also find out, like if I give this solar constant value and then radius of the sun and then mean sun earth distance and then sigma value, then we can find out like amount of energy emitted by the sun and then amount of energy received. Then this calculation will give you a temperature equivalent to black body temperature. Okay. We will also solve in the coming classes. Okay. So, this is air mass things. Normally 1.5 spectrum is something like this, and this is the spectrum at which we work. Okay. So, again we have some measuring instruments. So, quickly I will just browse through. Suppose if you have measuring instrument, it is well and good. You can get all the data. If you do not have, then what you will do? If I ask you to do the measurement for or do the calculation for solar energy calculation, then if you do not have data, then what you will do? You will see a place of similar climatic condition and take the data from that place. If that is also does not exist, then what you will do? You will use some kind of correlations. Okay. So, that will actually give you the radiation spectrum. That is how it is given. Okay. So it may be cloudless sky or maybe cloudy skies. Okay. And we have this kind of radiation you really expect in most of the cases, right? But you will have this kind of radiation. When cloud comes, it is very, very erratic and it is very difficult to predict, right? And if you consider a place, then always you will get this kind of things. Then how to design? That's a big thing. So if you know the characteristics, is always good. If your radiation is something like this, it is very difficult to design. Okay. And these are instruments I was talking about: heliometer, pyranometer. Then we have sunshine recorder. So these are the instruments normally we use for solar radiation purposes. Okay. And these are sensors we use because we need to know the knowledge of thermal conductivity, and then what is called we have thermocouple functions. So if you have two dissimilar metals and you keep the two different temperatures, it will generate EMF. Okay. So that principle we apply. Then when we consider pyranometer, what happens when solar radiation is falling and then there is a black surface where we will place this kind of heat sensors, and then other sensor is at the beneath, which is not affected by the radiation. Then EMF generated is actually converted in terms of watt per meter square. So that's how we do the calculation. Okay. So radiation we measure this way, like Langley, he was a famous scientist, and he first measured his spectral distribution, and that's how we know him. Like Langley is also a unit of solar radiation. There is one Langley is 1 calorie per centimeter square, which is equivalent to 1.163 into 10 to the power of -2 kilowatt hour per meter square. Okay. And you can see annual average solar radiation received in terms of Langleys, it's about 450 per day, and peak is about 600 Langleys, and in winter and monsoon it is about 300 to 400 Langleys. Okay. And you can see the radiation spectrum of India here. So red color means more, that is about 5.5 to 6 kilowatt hour per meter square. Okay. And in our place, even though it is not red very properly, but it's fine, our things will work actually, it's not a problem. 4.5 or 5 if you get, then it will also work best. Now something to go again. We have how much time normally we have? Pushpender, then tutorial is there. Maybe 10 minutes I can take, and then we can start that. So we have instantaneous and global flux, then hourly values. Sometimes what happens, even though radiation parameters or radiation informations are with us, actually these are not in a good form. Suppose your requirement is hourly, but the kind of data you have is the daily average data. So again you need to process it for your requirement. So that's how there is a need of studying those aspects, like daily global and diffuse flux incident over the whole days, then what happens, and then hourly what happens. Okay. So we need to study in different dimensions, like in watt per meter square, joule per meter square, but mostly what we are interested about insolation, which will give you watt per meter square is the reading. Okay. Now we have beam flux and equivalent beam flux. Suppose if solar radiation is coming here, okay, it is IBN and it is at certain angle, say theta or theta z, it is zenith angle. So it is equivalent is IBN cos of theta z. Okay, that's how it is. So beam flux is IBN, and then IBN cos phi cos theta 2 is the equivalent beam flux. Okay. So normally this theta is actually composed of many angles. Okay. So this is zenith angle theta 2. So this is radiation which is coming from the sun. It makes an angle of theta 2 with respect to the normal to the horizontal surface. Okay. And these are different angles which are related to this solar geometry. Okay. So, you have this globe, and these are the observer's meridian, okay, and this is the what is called different slabs. What you can say, we can just to define this latitude and longitude, this is equator, and if you want to write this one, this is like your longitude, and already I defined latitude, right? Okay, this is already known. Yeah, so declination already I defined, and it's like equinox and all. So delta actually mathematically you can say 23.45 sine of 360 by 365 284 plus n. So n is the nth day of the year, and once you know, say for example January 1, it will be n is equal to 1. So February 1, it will be 31 plus 1, 32. So that way you can count these n values, and you can find out delta. So delta values varies from minus plus 23.45 to minus 23.45. So 0 in where? In equinox days, right? Summer and winter, and other values you can say December and then June. Our angle, since it is 1 hour is 15 degree, okay. That means if we draw this, okay, and this omega is 0, okay, and this part it is positive from solar noon and is negative. What happens if we have to find out at 13 hours, this is actually 1 hour, and this is 15 degree, and sorry, I'll just cut it, otherwise it will be disturbing. It is minus 15 degree, okay, and if you have to find out at 11 o'clock, it will be plus 15 degree, okay. And if you are interested about 10:30, then what will happen? Half an hour is 7.5. So that way you can find out this hour angle, and it varies from minus 180 to plus 180. Okay. Just I will take. Say suppose if I consider a horizontal surface here, this is horizontal surface, and this is north, this is south, this is east, and this is west. Okay. So sun is here, solar radiation is falling here, and this is normal to the horizontal surface, okay, and this angle is your zenith angle, okay. And if we project on this line on the horizontal surface, and if we draw this, and this angle is your gamma s, and this is alpha s. This is altitude. This is altitude angle, and this is solar azimuth angle. This is solar azimuth angle. So here sun is here, and this beam flux makes an angle theta z with the normal to the horizontal surface. Okay, and I am projecting on the horizontal surface. Okay, towards due south. This angle is gamma s, and this angle is alpha s, and this is altitude angle. This is solar azimuth angle. Okay. Again, I will draw here to surface. Now I will define the surface azimuth angle. Okay. So this is important. Then I will just conclude. Few things I will discuss, maybe other. So we will have. We'll make something like this, and it makes an angle beta here. So one is perpendicular to the horizontal surface, other one is perpendicular to the normal surface, and this may be sun, and this will work something like this. So this is theta, theta and theta, these are different. This is theta and this is theta z, and this is normal to the inclined surface, because this is at certain beta, normal to the inclined surface. And this is normal to the horizontal surface. Okay. Already you know what is this. Okay. This is gamma s, and also you know this is alpha s, but this is gamma. This is surface azimuth angle. So what I have drawn here, this is the sun ray or beam flux, and it makes an angle theta with respect to the normal to the inclined surface, theta z with respect to the normal to the horizontal surface. Okay. So this theta z is always with normal to the horizontal surface. Okay. And then if you project on this horizontal plane, and what angle it makes is nothing but actually surface azimuth angle. Okay. Earlier what we have discussed is solar azimuth angle, right? And this alpha s is very important when we talk about beta values. Okay. And mostly this gamma is very important, and of course this is north, south, then east, and this is west. It's clear? All the things you will get actually in the slides. So slope is beta. I don't have to explain it now. Okay, it's a beta only, and already I have explained the geometry. So theta you will get is many angles. Okay, so origin you don't have to think much. So it will actually it will be expressed something like this. Okay, and based on the situations, this expression will be simplified to a very small expression. Okay. So I will just show some of the interesting thing, like what happens if it is vertical. Of course beta will be 90 degree. So if you substitute the beta value 90 degree, then you can redo the calculation. You can see it is very simple expression. And if it is along the due south, then gamma will be 0. So your expression will be something like this. So different situations you can actually modify the expression and do the calculation. It's very easy, right? So maybe no, I will not extend further. We need to solve some problem as well, and you need also break. Okay. So we can find out what could be this time, like length of the time, like what I mean to say, like sun, how long the sun will be there in a particular, and what is the maximum duration of sun hour. So that can also be find out by doing this calculation. It is like TD is 2 by 15 cos inverse of minus 10 delta and 10 phi. Okay. So this can be calculated, and you can find out if you know phi and delta, then you can find out what is duration TD of the day length. Fine. And in solar calculations, we never consider standard time. We consider solar time or local apparent time. So this local apparent time is standard time plus minus 4 LST minus LOC plus E. What is this 4 and E? Actually we need to have two corrections. And first is difference between the longitude of a location and a meridian on which the standard time is based, and this correction has a magnitude of 4 minutes for every degree difference in longitude. And equation time is due to the fact that Earth's orbit and rate of rotations are subjected to small variations, and the difference in minutes between the solar time and standard time can be something like this. Okay. And while doing the calculations, you must sure that which hemisphere you are doing the calculation. If you are in eastern hemisphere, then negative sign, and if it is western hemisphere, it is positive side. Okay, and then you can find out the standard formula is there to find out this E, and E what you will get in minutes, and you can find out. Okay. So, and Cleans has recommended some this. Normally what happens when you need to find the radiation spectrum, you need to know what is happening in every day. Okay, but it's very tedious to calculate the radiation spectrum, what is happening every day. So, what people have done, they have identified some representative days for January 1 day, February 1 day, and if you do the radiation calculation on that particular day, that means you are done. So, that will give you the radiation spectrum of particular month. Okay. So, that is how it is represented. March it is, sorry, January it is on 17th, February 16th, and again March 16th, and you can see the dates to be considered to know the representative day for a particular month. So, maybe I will stop here because these things will calculate in the coming tutorial things. Okay. So, thank you very much for your patience, and we will continue now for doing some problem. Okay. So, maybe I can give a 10 minutes break, then we will start. Thank you.